Hello, friends. Every time a school groups students by grade, every time a database filters records, every time a program checks if a value belongs to a category, there is one idea running quietly underneath all of it. That idea is a set. Sets are the foundation of logic, database theory, and programming. In this video, we are going to cover three things: what a set actually is, the main ways to represent one, and how membership tables let you verify set operations with precision. By the end, you will have a clear mental model that connects notation to diagrams to tables, all in one coherent picture. Let's get into it. All right, let's define the core idea. A set is an unordered collection of distinct elements. Unordered means the arrangement does not matter. Distinct means no element appears more than once. So the set containing 2, 5, the word cat, and the value true is a perfectly valid set. We write membership using the symbol that looks like a stylized E. 2 is in S, dog is not in S. The cardinality of a set, written as vertical bars around the name, tells us how many elements it contains. Set S here has a cardinality of 4. An empty set, written as a circle with a slash, contains nothing. Compare that to a multiset, which does allow repeated elements. Sets do not. That distinction matters everywhere in math and programming. Up next, let's look at the two standard ways to write a set down. Now let's talk about how we actually write sets down. There are two standard approaches. The first is roster notation. You simply list every element inside curly braces. A equals the set containing 2, 4, and 6. That is direct and easy to read when the set is small. The second set, B, is the set containing 6, 8, and 10. The second approach is set builder notation. Instead of listing every element, you describe a rule. A equals the set of all x such that x is even and x is less than 8. B equals the set of all x such that x is even and x is between 6 and 10, inclusive. The vertical bar is read as such that. Both notations describe the same sets. Set builder becomes essential when a set is infinite or defined by a complex condition. Next, let's see how to visualize these sets. Here's the interesting part. Once you have your sets written down, a Venn diagram lets you see their relationships at a glance. We have set A containing 2, 4, and 6, and set B containing 6, 8, and 10. Each set gets a circle inside a rectangle representing the universal set, U. Elements that belong only to A sit in the left region. Elements that belong only to B sit in the right region. The overlapping region holds elements in both sets. That overlap is the intersection. Here, only 6 lives there. The union covers everything in either circle, meaning 2, 4, 6, 8, and 10. Set A minus B, the difference, is what remains in A after removing shared elements, which is 2 and 4. These same three operations will come back in our membership table, so keep this picture in mind. Let me show you the membership table. It works just like a logic truth table, but for set membership. We list every element from the universal set down the rows. Then we mark a 1 if that element belongs to a given set, and a 0 if it does not. For element 2, it is in A, so A gets a 1. It is not in B, so B gets a 0. The union column gets a 1 because 2 is in at least one set. The intersection gets a 0 because 2 is not in both. A minus B gets a 1 because 2 is in A but not in B. Follow the same logic for every row, and the full picture falls out. Element 6 is the only row where both A and B equal 1, confirming that 6 is the sole member of the intersection. These tables make set operations mechanical and verifiable. Let's wrap everything up. All right, let's bring it all together. A set is an unordered collection of distinct elements. You can describe any set in three ways. Roster notation lists elements directly. Set builder notation defines a rule. A Venn diagram shows relationships visually across regions. Then membership tables give you a row-by-row, systematic way to verify what the union, intersection, and difference actually contain for every element. All three representations are describing the same underlying structure. They just give you different angles on it, and knowing when to reach for each one is the real skill. Our running example, set A containing 2, 4, 6, and set B containing 6, 8, 10, worked consistently across every tool. In the next video, we will use this foundation to explore set identities and how to prove them formally. See you there.